Hello. In this video, we will talk about the basics of statistical inference. This is the so-called sampling paradigm that you have also seen in one of the last lectures. In statistics, we consider a population of which we're interested in to infer some properties. But we can only do so by randomly sampling parts of that population because we cannot observe all the individuals exhaustively. In such a sample of size n, we only have limited information about the real quantity of interest. From a sample of size n, we therefore have to infer the property of the population that we are interested in. This is, of course, a process that is subject to so-called sampling variability, as we have also discussed in one of the first lectures. We have to use statistical techniques to make valid inferences despite this sampling variability. Sampling variability comes from the fact that we randomly sample a subset of the population. This is this scenario. For our statistical analysis and to understand the techniques that we will cover in the future lectures a bit better, it's often useful to think about not only a single study in which we perform the sampling like up here, but also take the point of view of a theoretical meta-study like this, where we imagine that we sample from the population repeatedly. So in the meta-study, we have the population, and then we draw repeated samples of the same size from that population. And analyzing how quantities of interest behave in this kind of meta-study helps us then to learn something about the quantities in the population. So for example, if we have very small samples and a small population, then we can actually exhaustively list all the possible outcomes and all the possible samples of a certain size. So imagine that we're interested in inferring the total cost of knee surgeries in women older than 65 years. So in this hypothetical example, 1/4 of the women in the study elects to have no surgery at all. 1/2 elects to have surgery in one knee, and 1/4 again elects to have surgery in both knees. If you have a surgery in one knee, this costs you $35,000 US, and in two knees, because some parts are the same for the same surgery, it just costs $60,000. So let's imagine you're working for an insurance company and you would like to know what can I reasonably expect the total cost or the expected costs in groups of 3 women to be. So because it's only 3 women, we can list exhaustively all the possible outcomes. And this is done here. So one possible sample, for example, is that none of the women wants any surgery done. Of course, for the insurance company, this is the cheapest sample because this doesn't incur any costs and in total also leads to a total cost of 0. You can calculate, according to these percentages here, that this scenario occurs with a probability of 1/64. But of course, you can have all variations, for example, this sample, where the first woman has a single surgery done and the other 2 women don't have any surgery done. And then the sample occurs a cost of $35,000 and occurs with a probability of 2/64. So in this case, we can list all the possible outcomes in the meta-study, all the possible samples exhaustively, and then calculate certain quantities of interest and their distribution. So for example, if we're interested either in the total cost or in the average cost per person, then we can calculate how frequently each of the different outcomes occur and also make graphs of these quantities. This distribution here is called the so-called sampling distribution, and usually we don't have access to it because we can't exhaustively list all the possible samples. In this case, we do, and we can use it to answer questions, for example, like what percentage of samples has a total cost higher than $150,000, which might be important for us so that we can have the proper amount of money set aside for being able to pay for that. When we don't have access to the exhaustive list of possible samples, then we have to do other tricks, and we will see that even then it's possible to make probabilistic statements about the average or the total of such operations. So if we go back to the sample mean, the sample mean we got to know as a descriptive statistic that tells us something about the location of our data on the axis. The sample mean is also an estimator of the respective population quantity. So for example, if we're interested in the height of female students in Germany, then we look at a certain sample, and the sample mean, we can also use that as an estimate of the respective population quantity, if our sampling procedure adheres to randomness and independence and so on. Now, if we imagine to be in a meta-study, if we imagine that we draw multiple samples of a certain size from the population, can we then make statements about the distribution of all the sample means? And this is the so-called sampling distribution. So imagine you have these multiple samples. Can we answer questions like, how close is the sample mean to the true mean? At least probabilistically. And it turns out we cannot give an answer to this particular question, but what we can do is we can answer the question, how close to mu is the sample mean likely to be? And this is because we can mathematically calculate the so-called sampling distribution. So for the sample mean, under some assumptions that we will go into detail later, the sample mean is unbiased. That means the mean of the sampling distribution of the sample mean is actually the true population mean. And we can also calculate its standard deviation. It's the true population standard deviation divided by the square root of the sample size. And it's a Gaussian distribution, like what we got to know in the last lecture. And this is useful to quantify certain aspects of the sample mean. You can see that in this overview here, you can see that sampling variability can be quite dramatic. So all of these distributions that you can see here come from are samples from a sampling distribution with mean 500 and standard deviation 110 or 120. Yet the samples look quite different. So given that sampling variability and this large amount of sampling variability, where can I expect the mean of my sample to lie? How can I quantify whether 550, for example, whether that is a large sample mean or not? And we can do that by converting the sample means to, for example, to z-scores according to the sampling distribution. What is important is that because the standard deviation of the sampling distribution depends on the number of samples, a larger sample size gives us a smaller standard deviation of the sampling distribution. So here, for the same data set, we simply increase the sampling distribution and then we simply increase the number of samples in the sample and then plot the sampling distribution. So here we have an n of 4, and if we divide the standard deviation of the sample by the square root of the number of samples in the sample, then we get 60. So it's a fairly wide distribution. If we have an n of 9, then we divide by the square root of 9, so we divide by 3, and we have an n of 40. The larger sample size gives us a smaller standard deviation of the sampling distribution. So for example, in our example that we just saw for the sampling variability, we had a mean of 500 and a standard deviation of 120. So if we look at samples of size 4, then the standard deviation of the sampling distribution will be 60, because 120 divided by the square root of 4 is 60. If we look at samples of size 9, this is already down to 40, because 120 divided by the square root of 9 is 40. And for samples of size 16, it even gets smaller to 30. So we can see as the sample size grows, how the width of these distributions shrinks. Basically, that means that as our sample size goes up, we can expect that the distribution of possible sample means across many repetitions of the sampling process will be closer and closer to the true mean. So the mean of a larger sample in any given experiment that we do is not necessarily closer to the true mean than the mean of a small sample. But the probability of that happening is higher. You can actually compute that for this particular sample here. And this is summarized in this table. So for a sample size of 4, the probability of the sample mean being between 450 and 550 is about 60%. For a sample size of 9, it's about 80%. For a sample size of 16, it's already higher than 90%. And finally, for a sample size of 64, it's basically 1. So you can see that a larger sample size does not guarantee your mean to be close to the true mean, but it makes it more likely. So now we have to be careful. We have quite some notation, or we have introduced quite some notation of different quantities, and it's very important to keep all of these different quantities apart. We have individuals in the population, and we call them Y, and we also call this, the individual data points that we measure in the sample Y. In the population, our mean is denoted with the Greek letter mu, and the standard deviation is denoted with the Greek letter sigma. In a sample, the same quantity is denoted as y bar and s. So the mean of the sample is y bar, and the standard deviation of the sample is s. Then in the situation of a meta-study, what we introduced in this lecture, we are also looking at a distribution of y bars across many different samples in a hypothetical meta-study. In this case, we denote mu sub y bar, and as the estimator, or as the mean as the estimator is unbiased, this is equal to mu. And the standard deviation of the sample mean in this meta-study is sigma y bar. And this is equal to sigma of the population divided by the sample size. We can look also graphically at these different distributions. So the population distribution in our example was a Gaussian distribution centered at 500 with a standard deviation of 120. It has the parameters, as we just said, of mu and sigma. The sample distribution in the data of a given sample is shown here as a histogram, and it has a mean y bar of 526.1 and a sample standard distribution of 113.7. This part is fairly clear. Now again, the setting of the meta-study. Across many different repetitions of that same sampling experiment we just saw, the sampling distribution of the sample mean has a mean of 500, that we know because the sample mean as an estimator is unbiased, and a standard deviation theoretically of 24, because the standard deviation of the population divided by the square root of the number of samples is 24. Think carefully whether you can explain these different concepts and keep them apart. So what happens if we have a non-normal population distribution? So one of the assumptions that underlies these computations, especially for small samples, is that your population distribution is normal. What happens in a case like this, where the population distribution is even bimodal? So most of the data fall within this bump, but there's a small bump with much higher values. This biases the mean to slightly larger values, as you can see. Due to a theorem called the central limit theorem, for large samples, this isn't so much of a problem. The central limit theorem states that sums of random variables tend to be Gaussian distributed, no matter what the population distribution is. So you can see the sampling distribution, this is derived by a simulation. You can see that the sampling distribution for samples of size 4 still clearly shows this bimodality. You can imagine this easily to happen, that when you generate samples of size 4 of such a bimodal distribution, there's quite a bit of samples that just sample from the big peak and where no individual sample is in the small peak. However, as you increase your sample size, this scenario will become much less likely. So already in samples of size 8, you can see that the sampling distribution still shows 2 peaks, but they are already much more connected. And as soon as you have a sample size of 32, the bimodality in the sampling distribution of the sample mean is almost gone. And then for larger sample sizes, like 128, these distributions look reasonably Gaussian. So due to the central limit theorem, we can even make statements about the population, the sampling distribution of the sample mean if our original population distribution was not Gaussian, as long as our sample size is large enough. So we discussed some basic aspects of statistical inference in this lecture, and we'll continue with more concrete examples in the next video. Thanks a lot.